Hi, I'm Andrew Eisler, part of Jamal's Your Buddies group in AE/ME 401, and we will be going over safety glasses testing, our experiment and results from this test. So, some necessary background information on eye protection and eye safety. The CDC reports that 2,000 workers every day sustain some sort of eye injury that requires medical attention. That is a huge number, especially considering the fact that 90% of all eye injuries are preventable, whether that be wearing safety glasses or other measures. Uh, Safety glasses, the American National Standard Institute standardizes and decrees different standards on safety glasses based off of different factors, whether that be impact protection or otherwise. We will be going over in our experiment the ANSI 87 Plus impact protection standards, as 70% of all workplace injuries come from some sort of debris, whether that be falling objects or sparks in the workplace. So, the guiding question in our experiment is: are ANSI 87 Plus designated safety glasses as protective as they claim? The ANSI Z87 Plus requires three different tests, those being a high mass impact test, a high velocity impact test, and a penetration test. And the glasses must pass these tests or show no damage after going through these tests. We will be verifying the high mass test and the penetration test in our experiment. On top of this, seeing if they pass the test, we'll be tracking and presenting the strain data from these tests to see how these impacts bend and change the eyeglasses that we're testing. And finally, we will be making visual observations on the effects of these impact tests.
Alright, so moving on to our test plan. Our first step in that was our experiment setup. So in that, we first taped the foam head to the ground or a flat surface so that it was facing upwards. For our experiment, we used a notebook. We taped the foam head down to that just so it would stay in place. We attached a power supply at 5 volts to the Wheatstone bridge just so it would have some power. We attached a multimeter across the Wheatstone bridge to record the resistance. And we used clamps to place the poster board tube above the foam head, directly above where the glasses would be tested, so this helped guide the impactor down onto the glasses. We also glued a strain gauge onto each pair of glasses to be tested, so part of this was to sand down the surface of the glasses just so that the strain gauge would have a better connection on there. Our second step in the test plan was to attach either impactor, depending on the test, to the bottom of the case. So this was either going to be the more blunt impactor or it was going to be the needle impactor. We also added weights to the case by removing the top section of the case. So the weights we used for this were the same ones from the strain gauge lab, and we were able to use them interchangeably just so that we could use different weights with the same impactors. Our third step was to calibrate the strain gauge, make sure strain gauges are secured on the lenses, and record a baseline resistance of the strain gauge from the multimeter. So a big part of this was that we had some hysteresis problems with the strain gauges sometimes, so they would kind of go up in value, but then when you bent the glasses back, they wouldn't go back to that original value, so we just had to make sure that the values were turning out okay. The fourth step was to weigh the combined load of the case and added weight, so just so that we knew how much weight we were actually dropping on the glasses. Step 5 was drop the weight from a height of 50 inches, so this is going to be from the top of the tube. When weight is dropped, a slow motion video was recorded so that the resistance during the drop can be analyzed. This just let us go back and make sure that we were getting the right resistance numbers and all of that. The sixth step was to calculate exit velocity using basic physics equations and record, just so that we could calculate like the impact energy and stuff like that for our analysis. Our seventh step was to record change in resistance and remark on any changes to the glasses. So this was just making sure like what kind of scratches were coming up during the needle test, seeing if the glasses broke. And then our eighth step was to vary specified weights for each trial. So depending on what we're doing, if it's the needle test or the impactor test, each trial is going to have a different weight to it, so we had to change those out. And then the last step was to repeat steps 1 through 8 for each test until all trials have been completed. Okay, so this is the setup that we used for our experiment. On the left, you can see kind of what we were thinking of doing for our experiment. You can also see the two impactors that we used. They're identical except for where the actual impactor hit the glasses, so you can see both the more blunt one, and you can also see the needle. In the middle image, you can see what our actual setup looked like when we were actually testing. So this includes a couple extra things like the Wheatstone bridge, the power supply, the multimeter, and you can also see us weighing one of the impactors before doing a test. And then on the right, you can see our Wheatstone bridge setup, where the power supply was connected, and how we got our measurements. So this is a list of the most important pieces of test equipment that we used for it. The first item is the 3D printed weight case. You can kind of see that in the image there. That's the white 3D printed parts that we used. Next up was the impactor. So the one in the image there is currently the more blunt one, and that's what we used for our first test. We also used a nail as one of our impactors, so that could be swapped out with the first impactor depending on the test that we were doing. We also got two foam heads. You can kind of see that in one of the images. So we got two so that in case one of them broke, we would have an extra as a spare. We also tested 3 pairs of safety glasses. We had some spares for those just in case one of them broke. We also used one weight set. Again, that was the one from the strain gauge lab that we did earlier in an earlier semester. We also had a poster board tube that helped to guide the impactor down so that we were hitting the glasses in the same spot every time. We also had strain gauges for each pair of glasses, and that was just so that we could get our measurements. We also used some clamps that was used just to hold the poster board tube down to a wall or something like that. We also had a breadboard, and that was just used to make our Wheatstone bridge. We used a power supply, again to get some power. We also used resistors just so that we could make our Wheatstone bridge, and we also used a multimeter. So this is the schedule that we followed for our experiment. It just covers everything from our first assignment to actually testing, and then doing our data analysis. So this is kind of the process that we followed to get the experiment done. Alright, and this was our budget. So our total came out to $72.96. So the first things that we bought were the safety glasses. So we bought 3 pairs for testing. The first pair came with a spare, so we had that just in case we needed that. We also bought the 2 foam heads just because we didn't have that available to us. And then we also have the rods and the jam nuts, and that was used for the assembly of the impactor.
For the results, before we could run each trial, we made sure to measure the resistance. This drop resistance value will be used later on in our experiment. In order to get the resistance value when the weight was dropped, we ended up recording each of the drops and then playing back the video to see the lowest value displayed on the multimeter. With the 2 resistance value measured, we then used equation 1 here, the first one, to calculate the resistance change. Once we obtained all the resistance changes, we then moved on to calculating the strain and deflection. In order to calculate the strain, we needed the gauge factor. For foil gauges, they have a gauge factor of approximately 2. Then, using the measured values, we plug them into equation 2 here, which is just the change in the resistance over the original resistance multiplied by the gauge factor. In order to find the deflection, we need the gauge length. This was found to be 3 millimeters, and then we then used equation 3 here to find the deflection, which was the strain multiplied by the gauge length, and the deflections came out to be in millimeters. So the impact and penetration test conducted on the 3 safety glasses did provide valuable insight into their behavior under the Z87 safety requirements. All of the glasses successfully withstood the required forces without failure, which confirmed their high impact and penetration resistance standards. Of the models tested, the No-Cry exhibited the lowest deflection and strain values under both of the weighted tests. This indicates a solid balance between the material's strength and its flexibility. The worst were the radians, which had the highest deflection values, which suggested potentially lower stiffness. And to better analyze the data, we have taken the no-cry data and tabulated it here with the two plots. The first one is the pointed weight versus the deflection, and the second is the needle weight versus the deflection. In our experimental system, measurement uncertainty is inevitable because of the limitations given by the equipment used. The strain gauge is the greatest source of uncertainty, as many factors influence its measurements. Bonding the gauge incorrectly, thickness of the adhesive, or faulty wiring could give inaccurate results. And the multimeter does have a finite resolution of approximately plus or minus 0.1 ohms. This is substantial as the deflection calculation relies off of small changes in the resistance. And with the drop test itself, the height at which the weight was dropped impacts the deflection value. Even though the height was kept constant throughout each of the trials, there were still some expected variations in drop height as it was dropped by hand. Even a 1 centimeter difference could cause a small change.
So after looking at all of our data and all of our results, our glasses did pass the original hypothesis, which was, do they hold up to ANSI Z87 plus safety requirements? And we found that they did. All the glasses do actually hold up. And we found an interesting trend was that the most expensive pair did perform the best. So that there is, kind of bang for your buck with this, and they performed in the order of their cost. So the cheapest ones performed the worst, with the most expensive performing the best. And we saw this across our, price range. So that kind of brings up a point of like, well, what about these more expensive glasses is making them perform better? Is it the materials? Is it the build? What is causing this? I think it's also important to mention that throughout our results, we kind of found, a non-insignificant amount of uncertainty within our experiments. The strain gauges had an uncertainty of about 0.1 ohms. And because these strain gauges are really sensitive and a little bit of voltage change is a lot of, strain and stress in these parts, that could be a lot. That could end up being, pretty significant. That could bring our top glasses down to on par with everything else if they all had that same uncertainty. So that's something to think, to keep in mind. Another thing is that we used multiple different strain gauges during this experiment, which kind of brings up questions about hysteresis error and repeatability. And the thing is, there's not really a great way to determine how much those errors could have compounded. Did they exist? How bad was it? Did it not exist at all? We can't really see those things from the way that we performed our tests, and they weren't things that we took into account before performing the test to account for. So, we have different strain gauges. Do they all measure the same? Are they all as sensitive? Or do some have weak spots, dead spots? When a strain gauge would break during a test, was it failing in the test beforehand? Would that throw off test before that point? Again, we don't really know. Another future experiment should look at examining the validity of our data, kind of like our viscosity test. Can people repeat our experiments, get the same results with what we've done? Was it a good test, or was it just a test for the sake of testing? And another thing is that we use the same pairs of glasses throughout all the tests. So each weight, we went from like 100 to 600 grams. Each one pair of glasses, we had one cheap, one medium, one expensive pair, and that was used for all the tests with the blunt and all the tests with the sharp point. Could it have induced fractures or scratches that weakened the glasses that we would see in later tests? Maybe they're bending more than they would have initially. So that's something to think about too. For next steps, if we were to continue doing this, or if another group were to pick up on this, contact glasses manufacturers, get the data that they have, find out what their testing says, see were we close, were we off, was there some fatal error that we didn't even account for or find, was there like an unseen phenomena within these glasses that because of the way that we performed it and because of the things that we used, we just weren't able to see. And I want to see future groups look into why we saw such a difference between the most expensive and the cheapest pairs of glasses. Was it the quality of the materials? Was it the types of materials? Was it the type, the way they were built? Is there, sometimes you have the glasses that go over glasses like these, and then sometimes you have the ones that fit closer for people who don't have to wear glasses. Is there a strength difference in those. Are there different ways that those are going to behave that is going to affect the results that we got? So ultimately, all the glasses did pass. We proved our hypothesis, but the work is never over. So thank you.